Welcome to Sleepy Space. Tonight, we'll explore one of the strangest possibilities in modern cosmology. What if our galaxy is drifting inside a gigantic cosmic hole, a vast region of the universe containing far less matter than it should? Even more intriguing, scientists still don't know exactly why it exists. Let me know where you're listening from tonight, and if you enjoy these deep cosmic journeys, please like and subscribe. Now, settle in, and let's step into one of the universe's greatest mysteries. Before we can ask whether we are inside a cosmic hole, we have to slow down enough to understand what those words actually mean in the language of modern cosmology. Because the image that immediately forms in our minds is often misleading. A hole suggests an absence, a cavity, a place where something should be but is not. It evokes a dark opening in the ground, a gap in a wall, a missing piece in a structure. Yet, when astronomers speak about enormous voids in the universe, they are not describing emptiness in the everyday sense. They are describing regions where matter exists, galaxies exist, dark matter exists, radiation passes through, gravity still operates, and space itself continues expanding, but where the density of matter appears lower than the cosmic average. Tonight, as the Earth turns quietly beneath us, and the familiar stars seem fixed in their ancient positions, we begin with a possibility that would have sounded strange even to many astronomers a century ago. The possibility that our entire galactic neighborhood may reside inside a vast, underdense region of the cosmos, a region so large that light itself requires hundreds of millions or even billions of years to cross it, and so subtle that no human being living beneath the night sky could ever notice it without the combined efforts of generations of scientists, telescopes, mathematical models, and spacecraft. To appreciate why this idea emerged, it helps to remember that the universe revealed by modern observations is not arranged like evenly scattered grains of sand. On the largest scales accessible to observation, matter forms an intricate cosmic web. Galaxies gather into groups, groups gather into clusters. Clusters connect through elongated filaments stretching across unimaginable distances. These filaments weave together into walls and sheets, while between them lie immense regions containing far fewer galaxies than expected. The result resembles a three-dimensional foam frozen in time, with luminous structures tracing the boundaries and vast, emptier chambers occupying the spaces between. This architecture did not arise randomly. Its roots appear to reach back to tiny fluctuations present in the early universe, fluctuations measured today in the faint glow of the cosmic microwave background. Quantum-scale irregularities during the earliest moments of cosmic history were stretched by inflation to astronomical scales, creating slight differences in density. Gravity then amplified those differences over billions of years. Regions that began slightly denser attracted more matter, becoming denser still. Regions that began slightly less dense gradually lost matter to their surroundings. The rich became richer, the poor became poorer. The cosmic web emerged as the natural consequence of gravity operating across deep time. Within this framework, voids are not anomalies, they are expected outcomes. Yet the possibility that our own location may sit inside an unusually large, underdense region introduces a more provocative question. Not merely whether voids exist, but whether our particular cosmic address is influencing our understanding of the universe itself. The story begins with an assumption so fundamental that it often passes unnoticed. Modern cosmology relies heavily on the cosmological principle, the idea that when viewed on sufficiently large scales, the universe is homogeneous and isotropic. In simpler language, no region is fundamentally special. Any local irregularities should average out if one zooms far enough outward. This principle does not claim that every location contains identical structures. Clearly, it does not. Galaxies, stars, planets, and people exist in some places and not others. Rather, it suggests that the statistical properties of the universe become uniform when examined across immense distances. For decades, observations largely supported this view. Yet as astronomical surveys improved, researchers began noticing hints that the local universe might be somewhat less crowded than expected. Large galaxy surveys revealed fewer galaxies in certain nearby regions than cosmological models predicted. Measurements of galaxy distributions suggested that the density of matter around our location could be lower than the average density inferred from observations of much larger cosmic volumes. This possibility gradually evolved into what some researchers call the local hole, or, in a more specific formulation, the KBC Void, named after Ryan Keenan, Amy Barger, and Lennox Cowie, whose work attracted attention by suggesting that the local universe might indeed be underdense on remarkably large scales. The scale involved is difficult to grasp. We are not discussing the absence of a few galaxies. We are discussing a region potentially spanning hundreds of millions of light-years, perhaps even approaching 1 billion light-years in diameter, depending on the model and assumptions employed. Within such a region, the average density of matter might be significantly below the cosmic mean. Importantly, this would not mean we occupy the center of an empty sphere. The Milky Way remains surrounded by neighboring galaxies. The local group still exists. Nearby clusters remain visible. The underdensity would emerge statistically, only becoming apparent when enormous volumes are compared against the broader universe. One reason this idea fascinates cosmologists is that location matters in gravitational systems. Gravity is not merely a force pulling objects together. Within general relativity, gravity reflects the geometry of space-time itself. The distribution of matter influences how space-time evolves. If a region contains less matter than average, its expansion history can differ slightly from that of denser regions. Over vast timescales, even small differences may accumulate into measurable effects. This leads us toward one of the most intriguing puzzles in contemporary cosmology, although tonight we only glimpse its edge. Different methods of measuring the expansion rate of the universe produce values that do not perfectly agree. One method examines the early universe through the cosmic microwave background. Another studies nearby galaxies and supernovae. The discrepancy is not enormous, but it is persistent enough to command serious attention. Some researchers have wondered whether a local underdensity could contribute to this tension. If we reside within a region that expands slightly differently from the cosmic average, then observations made from our location might produce subtly biased conclusions about the larger universe. Whether this explanation proves sufficient remains uncertain, but the question itself illustrates why cosmic geography matters. Suddenly, the possibility of living inside a vast, underdense region is no longer merely an interesting detail. It becomes a factor that could influence humanity's attempt to measure the age, size, and evolution of the cosmos. Yet caution is essential. Scientific progress often advances through possibilities that later prove incomplete. Not all studies support the existence of a giant local void. Some analyses find evidence for underdensity, but suggest a smaller magnitude. Others argue that observed galaxy distributions remain compatible with standard cosmological expectations. Still others point to observational biases, survey limitations, and statistical uncertainties that complicate interpretation. The challenge is immense, because we cannot step outside the universe to obtain an external perspective. Every measurement originates from within the structure we are trying to understand. astronomers must reconstruct the three-dimensional distribution of matter from incomplete observations, finite survey volumes, and light that has traveled for millions or billions of years before reaching our instruments. In a sense, cosmology resembles archaeology performed across time rather than space. Every photon arriving at a telescope carries information from a different era. The farther we look, the farther back we travel into history. Mapping the universe, therefore, requires combining countless fragments into a coherent picture, much as an ancient mosaic must be reconstructed from scattered pieces. What makes the idea of a cosmic whole especially captivating is that it challenges intuition without abandoning established physics. No exotic dimensions are required. No violations of relativity are necessary. No speculative technologies enter the story. Instead, the possibility emerges naturally from known processes of structure formation. Gravity gathers matter unevenly. Dense regions grow denser. Sparse regions grow sparser. Given enough time, enormous voids become inevitable. The real question is not whether such structures can exist. We know they can. The question is whether one of them happens to encompass our own location, and whether its influence is large enough to matter. As the night deepens and the imagination drifts beyond the Milky Way, beyond nearby galaxies, beyond clusters and filaments, into the largest architecture ever discovered, the phrase cosmic whole begins to lose its dramatic edge and acquire something more interesting. It becomes not a void of meaning, but a clue that the universe may be less uniform around us than we once assumed. A clue that our position in the cosmic web might subtly shape our observations, and perhaps most intriguingly, a clue that the next breakthrough in understanding the universe may not come from looking farther away, but from understanding more clearly the enormous quiet region in which we already reside. The possibility remains unresolved, suspended between evidence and uncertainty. But that uncertainty itself is part of the wonder. For if we truly are inside a cosmic whole, then the story is not merely about a missing quantity of matter. It is about perspective. It is about how a civilization living on a small planet inside an ordinary galaxy attempts to determine whether its own neighborhood is misleading it about the nature of reality, and how the answer to that question may be hidden not in the brightest structures of the cosmos, but in the vast, silent spaces between them. If the idea of living inside a cosmic whole feels strange, it is because the human mind naturally imagines the universe as a place filled with objects rather than shaped by absences. We notice stars, galaxies, glowing nebulae, clusters blazing across hundreds of millions of light years. Yet modern cosmology has gradually revealed something far more surprising. The largest structures in existence are not necessarily the things that shine. They may be the enormous regions where comparatively little exists at all. To understand what a cosmic void truly is, we must set aside the familiar image of outer space as a uniform ocean sprinkled evenly with galaxies, and instead enter a universe whose architecture resembles something far more intricate, almost biological in appearance. A colossal network woven across billions of light years, where matter gathers into filaments and walls, while vast, silent chambers open between them. These chambers are what astronomers call cosmic voids, and although the word void suggests emptiness, that description is only partially accurate. A cosmic void is not a hole punched through reality, nor is it a region where space disappears. It is better understood as a volume of spacetime whose average density of matter is significantly lower than the cosmic mean, a subtle distinction that becomes increasingly important as we move deeper into the mathematics and physics that govern large-scale structure formation. Imagine drifting far beyond the Milky Way, beyond the local group, beyond the Virgo cluster, until individual galaxies begin to merge visually into faint threads of light stretching across darkness. At this scale, the universe ceases to resemble a random scattering of islands and begins to resemble a vast three-dimensional web. This cosmic web, first predicted through gravitational simulations and later confirmed through increasingly sophisticated galaxy surveys, emerges naturally from the interaction between gravity and primordial density fluctuations left behind by the early universe. In the aftermath of cosmic inflation, tiny variations in density existed throughout space. These variations were extraordinarily small, differing by roughly 1 part in 100,000. Yet gravity is patient. Given enough time, even the smallest imbalance becomes significant. Regions that began slightly denser exerted stronger gravitational attraction, drawing in additional matter and becoming denser still. Regions that began slightly less dense gradually lost matter to their surroundings. This process, sometimes described through gravitational instability theory, transformed nearly uniform matter distributions into the filamentary structures observed today. The mathematics underlying this transformation originates in perturbation theory, fluid dynamics, general relativity, and statistical cosmology, but the visual result can be understood intuitively. Matter flowed downhill through gravitational landscapes toward increasingly dense valleys, leaving behind expanding basins of lower density. Those basins became the cosmic voids. What makes this process fascinating is that voids do not merely sit passively between galaxies, they evolve. In some respects, they evolve more dramatically than dense regions themselves. A cluster of galaxies grows by accreting matter, but a void grows because matter escapes from it. The underdense region expands faster than the average cosmic expansion, effectively evacuating itself over billions of years. In simplified terms, if gravity acts like a financial system, overdense regions accumulate interest, while underdense regions fall progressively into deficit. The contrast between rich and poor increases with time. This phenomenon emerges naturally from solutions to Einstein's field equations when matter is distributed unevenly. Space does not expand identically everywhere. Local density influences local dynamics. Consequently, voids become larger, emptier, and more geometrically distinct as cosmic history unfolds. Observationally, identifying a void is not as simple as finding a blank patch in the sky. The challenge arises because astronomy observes light rather than matter directly. Most matter in the universe is believed to be dark matter, which neither emits nor absorbs light in detectable ways. Galaxies serve as tracers, revealing where gravitational structures likely exist. By mapping the three-dimensional positions of millions of galaxies through redshift surveys, astronomers reconstruct the distribution of matter across enormous volumes. Projects such as the Sloan Digital Sky Survey transformed this effort from speculation into precision science. When these surveys produced detailed maps, researchers discovered that galaxies arrange themselves into interconnected filaments surrounding vast regions containing far fewer galaxies than expected. Some voids span tens of millions of light-years. Others extend across hundreds of millions. Their shapes are often irregular rather than spherical, reflecting the complex geometry of the surrounding cosmic web. Yet, despite their apparent emptiness, voids are not entirely empty. Hydrogen gas remains present. Dark matter remains present. Occasional galaxies drift through them. Even radiation from distant quasars passes across their interiors. The term void, therefore, describes relative scarcity rather than absolute absence. This distinction becomes crucial because absolute emptiness, in the strict physical sense, may not exist anywhere in the observable universe. Quantum field theory suggests that even the most perfect vacuum possesses fluctuating fields and transient particle activity. Space itself is never truly blank. Instead, every region contains some level of physical structure, however sparse. As cosmologists refined their understanding of voids, they began recognizing that these regions offer unique scientific opportunities. Dense environments such as galaxy clusters are extraordinarily complicated. Gravitational interactions, mergers, shock waves, magnetic fields, and active galactic nuclei all overlap simultaneously. Voids, by contrast, provide cleaner laboratories. Because gravitational influences are weaker and structures are simpler, certain cosmological effects become easier to isolate. Researchers use voids to test models of dark energy, alternative theories of gravity, neutrino masses, and the growth of cosmic structure. Some modified gravity theories predict subtle differences in how matter behaves within underdense environments. Consequently, mapping voids has evolved from a descriptive exercise into a powerful experimental tool. The geometry of voids also introduces an unexpectedly elegant connection between cosmology and mathematics. Large-scale structure analysis frequently employs concepts from topology, graph theory, Voronoi tessellations, and computational geometry. Rather than merely counting galaxies, scientists study the shapes of regions between them. The universe becomes a geometric object whose connectivity, curvature, and statistical architecture reveal information about its origin. In this sense, voids are not gaps in the cosmic story. They are part of the story's grammar. Without them, the web itself could not exist. Their boundaries define the locations of filaments, just as valleys define mountain ranges by contrast. The relationship between matter and emptiness becomes inseparable. Historically, the recognition of voids represented a profound shift in cosmological thinking. Earlier generations of astronomers often assumed that galaxies were distributed more or less uniformly on large scales. During the 20th century, increasingly comprehensive observations began challenging this assumption. By the late 1970s and early 1980s, evidence accumulated for structures such as the Boötes void, one of the first giant voids to attract widespread attention. Spanning roughly 330 million light-years, it appeared astonishingly empty compared with surrounding regions. Its discovery forced researchers to confront the possibility that the universe's architecture was far more dramatic than previously imagined. Subsequent surveys revealed that such structures were not anomalies, but components of a larger pattern extending throughout the observable cosmos. Today, simulations containing billions of particles reproduce this web-like structure with remarkable fidelity, reinforcing the idea that voids arise naturally from the known laws of gravity acting on primordial fluctuations. Yet, despite these successes, cosmic voids continue to provoke deeper questions. One of the most intriguing concerns the relationship between local environments and global observations. If observers happen to reside within an unusually large, underdense region, measurements of cosmic expansion could potentially differ from those obtained by observers located elsewhere. This possibility remains an active area of research and is one reason discussions of local voids attract attention. It does not imply that established cosmology is fundamentally wrong. Rather, it highlights the subtle challenge of interpreting observations made from a single location within an immense and structured universe. Every measurement possesses context. Every observation emerges from somewhere. As our maps become increasingly precise, cosmologists continue asking whether our particular location introduces biases that must be understood. Beneath all these technical details lies a quieter realization. The discovery of cosmic voids altered humanity's picture of existence in a subtle but profound way. For centuries, people imagined the universe primarily through its visible inhabitants, stars, planets, galaxies. Yet, on the largest scales, the arrangement of those luminous structures may be governed as much by what is absent as by what is present. The cosmic web is not merely a network of matter. It is a partnership between accumulation and evacuation, between gathering and dispersal, between gravity's ability to build structures and its simultaneous ability to create vast realms of relative emptiness. Looking outward across billions of light years, one begins to understand that the universe is not a crowded city stretching endlessly in every direction. It is something closer to an immense cathedral of space, where the grandest chambers are often the quietest ones, where darkness acquires structure, and where the largest features ever discovered are not mountains of matter, but oceans of remarkable scarcity. In that context, a cosmic void becomes more than an astronomical object. It becomes a reminder that understanding reality sometimes requires studying what appears missing, because the shape of absence can reveal as much about the universe as the brightest galaxies ever could. As we drift deeper into the possibility that our cosmic neighborhood may not be entirely typical, the discussion narrows from the broad concept of voids to a far more intimate and unsettling question. What if the underdense region is not somewhere out there among distant galaxies, but here, surrounding us right now, on scales so vast that the Milky Way itself becomes almost invisible within the larger structure? This is where two names begin to appear repeatedly in modern cosmological literature, names that sound deceptively simple when compared to the immense implications hidden behind them: the local hole and the KBC void. Neither term refers to a confirmed object in the same way that a planet or galaxy cluster can be confirmed. Instead, they describe an evolving scientific possibility, a statistical pattern emerging from decades of observational surveys, a potential feature in the distribution of matter surrounding our location in the universe. To understand why these ideas attracted serious attention from cosmologists, we must first appreciate a subtle challenge hidden within almost every astronomical measurement ever made. When astronomers attempt to understand the universe as a whole, they are forced to observe it from a single point inside it. Unlike a cartographer mapping a continent from orbit, humanity has no external vantage point from which to inspect the cosmic landscape. Every measurement originates from Earth, from the solar system, from the Milky Way, from a particular location embedded within a specific region of the cosmic web. This creates a profound methodological question. How typical is our neighborhood? The assumption that we occupy no special position is deeply woven into modern cosmology through the Copernican principle, which extends the philosophical lesson of Nicholas Copernicus far beyond the solar system. Just as Earth is not the center of the solar system, and the solar system is not the center of the galaxy itself is presumed not to occupy a privileged location in the universe. This principle has been extraordinarily successful because it prevents cosmology from becoming trapped by anthropocentric assumptions. Yet, it is important to recognize that the Copernican principle is statistical rather than literal. It does not require every location to be identical. It only suggests that any particular location should not be extraordinarily special when viewed on sufficiently large scales. The possibility of a local hole emerged precisely because astronomers began asking whether our local environment might be somewhat less representative than previously assumed. During the late 20th century and early 21st century, increasingly comprehensive galaxy surveys started revealing hints that the density of galaxies within several 100 million light-years of Earth appeared lower than expected when compared to larger cosmic volumes. These observations did not immediately imply the existence of a giant void. Galaxy counts are affected by observational biases, dust obscuration, distance uncertainties, selection effects, and statistical fluctuations. Nevertheless, as data accumulated, a recurring pattern appeared difficult to ignore. Some surveys suggested that nearby space contained fewer galaxies than models predicted if matter were distributed uniformly on those scales. The significance of this possibility increased dramatically when researchers Ryan Keenan, Amy Barger, and Lennox Cowie published work suggesting that the local universe may reside inside a remarkably large, underdense region. Their analysis examined galaxy luminosity densities across different distances and reported evidence consistent with a substantial deficit of matter extending across scales approaching 1 billion light-years. The structure became informally known as the KBC Void, named after the initials of the researchers involved. What made the proposal fascinating was not merely its size, but its potential implications. If correct, the KBC Void would rank among the largest known structures associated with our local cosmic environment. Yet describing it as a whole can be misleading. No boundary wall surrounds it. No abrupt transition separates the interior from the exterior. Instead, the concept is statistical. Imagine standing inside a vast forest, where the trees gradually become denser as you move outward. At no point would you cross a fence marking the forest's edge. The change would emerge only after measuring tree density over enormous distances. The KBC Void operates similarly. Galaxies still exist within it. Clusters still exist. Filaments still exist. The defining feature is that the average matter density may be lower than the cosmic mean when examined across sufficiently large volumes. The geometry of such a structure introduces intriguing complexities. Early discussions sometimes visualized the void as approximately spherical, largely because spherical models simplify calculations. However, the actual universe rarely produces perfect geometric forms. Large-scale structures emerge from chaotic gravitational evolution, influenced by countless interacting variables. Modern simulations reveal that voids often possess irregular shapes, elongated axes, nested substructures, and evolving boundaries. Consequently, even if a local underdensity exists, its precise morphology remains uncertain. Some analyses suggest multiple overlapping underdense regions rather than a single clean cavity. Others indicate gradients in density rather than sharply defined voids. This uncertainty reflects a broader truth about observational cosmology. Reality often resists the simplicity of theoretical diagrams. Yet, despite these complications, the possibility remains compelling because of its connection to one of the most discussed puzzles in modern astrophysics. For several years, measurements of the Hubble constant have produced values that differ depending on the method employed. Observations based on the early universe, particularly analyses of the cosmic microwave background, combined with the standard lambda-CDM cosmological model, tend to yield one value. Measurements derived from relatively nearby supernovae and other local distance indicators tend to produce a somewhat larger value. The discrepancy is not catastrophic, but it persists beyond what many researchers would expect from random measurement errors alone. This situation, commonly known as the Hubble Tension, has inspired a remarkable range of proposed explanations. Some invoke new particle physics. Others explore modifications to dark energy. Still others investigate potential systematic errors hidden within observational techniques. The local hole hypothesis entered this discussion because local density influences gravitational dynamics. In an underdense region, matter exerts less gravitational deceleration than average. Consequently, local expansion rates can differ slightly from those expected in denser environments. In simplified terms, galaxies near the center of an underdense region may appear to recede somewhat faster relative to local expectations because surrounding matter exerts weaker gravitational restraint. If observers happen to reside within such a region, measurements of cosmic expansion based on nearby objects could potentially be biased toward larger values. This possibility does not automatically solve the Hubble tension. Many studies suggest the effect may be insufficient to explain the entire discrepancy. Yet the fact that such a connection exists at all demonstrates how deeply local structure can influence our interpretation of universal phenomena. What appears at first to be a question about galaxy density gradually becomes a question about the reliability of cosmological inference itself. The mathematical framework behind these ideas traces back to solutions of Einstein's field equations describing inhomogeneous universes. While the standard Friedmann-Lemaitre-Robertson-Walker metric assumes large-scale homogeneity, alternative models, such as Lemaitre-Tolman-Bondi solutions, allow matter density to vary with position. These models provide useful tools for exploring how local underdensities affect observable quantities such as redshift distance relationships, luminosity distances, and expansion rates. Importantly, most cosmologists do not view such models as replacements for the standard cosmological framework. Rather, they serve as laboratories for understanding how deviations from perfect homogeneity influence observations. In this sense, the local hole functions as a bridge between idealized cosmological assumptions and the messy complexity of the real universe. The observational challenge remains formidable. Mapping matter on these scales requires surveys spanning enormous volumes while maintaining high completeness and precise calibration. Astronomers rely on infrared observations, spectroscopic redshift catalogs, galaxy luminosity functions, weak gravitational lensing analyses, peculiar velocity measurements, and increasingly sophisticated statistical methods. Different datasets sometimes produce different conclusions because each probes matter distribution through a different physical mechanism. This diversity of approaches is not a weakness, but a hallmark of healthy scientific investigation. When evidence converges from independent methods, confidence grows. When discrepancies appear, researchers gain opportunities to refine models and uncover hidden assumptions. As of today, the existence of some degree of local underdensity remains plausible within portions of the scientific literature, but the precise size, depth, and significance of that underdensity continue to be debated. This uncertainty should not be mistaken for failure. Cosmology advances by quantifying uncertainty, not eliminating it prematurely. The deeper significance of the local hole and KBC void may ultimately extend beyond whether either structure reaches a specific statistical threshold. Their true importance lies in the reminder that the universe possesses layers of structure large enough to influence the interpretation of cosmic history itself. For centuries, humanity's challenge was discovering that Earth was not the center of the cosmos. Today, the challenge is subtler. We know we are not central, yet we continue asking whether the particular regions surrounding us might still matter in ways we have not fully understood. Somewhere beyond the glow of nearby galaxies, beyond the Virgo cluster, beyond the familiar landmarks of local space, the density of matter may gradually increase until our neighborhood appears, in retrospect, like a quiet depression in an otherwise richer cosmic landscape. Whether that picture ultimately proves correct remains unresolved. But as the universe expands through the darkness and ancient photons continue their silent journeys toward our telescopes, the local hole remains one of those rare scientific ideas that feels both deeply technical and strangely intimate, because it asks not merely what the universe is, but where exactly within that universe we happen to be standing. The moment we ask whether our region of the universe contains fewer galaxies than expected, we encounter one of the deepest observational challenges in all of science. Because unlike a geologist surveying a valley or an oceanographer mapping a coastline, a cosmologist cannot step outside the system being studied. Every galaxy map, every measurement of distance, every estimate of density begins from a tiny rocky planet orbiting an ordinary star within a spiral galaxy that itself occupies only a microscopic corner of the observable universe. This creates a strange intellectual situation. We are attempting to determine whether our cosmic neighborhood is unusually empty while being trapped inside that neighborhood. And yet, over the past several decades, astronomers have developed methods so sophisticated that they can transform faint points of light into a three-dimensional map stretching across billions of light years. To understand how researchers can even begin investigating something like the local hole or the KBC Void, we must first understand a simple but profound reality. Astronomers do not directly observe the structure of the universe. They observe light. Everything else must be inferred. When a telescope points toward a distant galaxy, it does not receive a label indicating distance, mass, velocity, or environment. It receives photons, particles of light that have traveled across space and time before ending their journey on a detector. The challenge is converting those photons into a reliable description of cosmic geography. This process begins with one of the most important discoveries in modern astronomy, the realization that the universe is expanding. As space expands, light traveling through it becomes stretched, increasing its wavelength and shifting it toward the red end of the electromagnetic spectrum. This phenomenon, known as cosmological redshift, provides astronomers with a powerful proxy for distance. In general terms, the larger the redshift, the farther away a galaxy tends to be. The relationship is not perfectly simple because local gravitational motions introduce complications, but redshift remains one of the fundamental tools for constructing large-scale maps of the cosmos. Imagine standing in a vast, dark field filled with lanterns. If every lantern emitted a characteristic color, and that color shifted predictably with distance, you could estimate where each lantern was located without physically traveling to it. This is essentially what astronomers do with galaxies. By measuring the spectra of millions of galaxies, researchers build three-dimensional catalogs that reveal not only where galaxies appear on the sky, but also how far away they are likely to be. The resulting maps are among the most extraordinary achievements in human intellectual history. Structures hundreds of millions of light years wide emerge from datasets composed entirely of tiny traces of light. Yet mapping galaxies is only the beginning. The existence of a void cannot be established merely by noticing an empty-looking region on a map. The universe is too large and too statistically complex for such visual impressions to be reliable. Instead, astronomers must determine whether the number of galaxies observed within a given volume differs significantly from what cosmological models predict. This requires a concept known as number density, which measures how many galaxies occupy a particular region of space. If a volume contains substantially fewer galaxies than expected, it may indicate an underdensity. However, immediately another complication appears. Not all galaxies are equally visible. Bright galaxies can be observed from enormous distances, while faint galaxies disappear beyond the limits of a survey. A naive galaxy count, therefore, risks producing misleading conclusions. To overcome this problem, astronomers employ luminosity functions, statistical descriptions of how galaxy brightness is distributed throughout the universe. By understanding how many faint galaxies should exist relative to bright ones, researchers can correct for observational incompleteness and estimate the true underlying population. This transition from raw observation to statistical reconstruction marks one of the defining characteristics of modern cosmology. The universe is rarely observed directly. It is inferred through layers of probability, modeling, calibration, and cross-validation. As surveys became increasingly sophisticated, projects such as the Sloan Digital Sky Survey, the 2-micron All-Sky Survey, and later large spectroscopic programs began revealing the detailed architecture of nearby space. These surveys did not simply count galaxies. They measured positions, redshifts, luminosities, morphologies, and environments across enormous cosmic volumes. The resulting datasets allowed researchers to calculate galaxy density as a function of distance from Earth. It was through analyses of this kind that some investigators began noticing evidence suggesting the local universe might contain fewer galaxies than regions farther away. Yet even this conclusion remained far from straightforward, because galaxies themselves represent only a fraction of total matter. Most of the universe's matter appears to be dark matter, invisible to conventional telescopes. A region with fewer visible galaxies does not automatically imply a proportional deficit of total mass. Consequently, astronomers sought additional methods capable of probing matter distribution more directly. One of the most elegant emerged from Einstein's theory of general relativity. According to relativity, mass bends spacetime, and bent spacetime alters the path of light. This effect, known as gravitational lensing, allows researchers to infer the presence of otherwise invisible matter. When light from distant galaxies passes through large-scale structures, subtle distortions appear in the observed shapes of those galaxies. By statistically analyzing millions of such distortions, cosmologists can reconstruct maps of mass distribution, including contributions from dark matter. Weak gravitational lensing has become one of the most powerful tools for investigating whether underdense regions correspond to genuine deficits in total matter, rather than merely deficits in visible galaxies. Another line of evidence comes from peculiar velocities, motions that deviate from the smooth expansion of the universe. In a perfectly uniform cosmos, galaxies would move apart according to the Hubble flow. In reality, gravitational attractions generated by matter concentrations create additional motions superimposed on the expansion. Galaxies fall toward overdense regions and move away from underdense ones. By measuring these deviations, astronomers can infer the underlying gravitational landscape. A sufficiently large void should influence the motions of surrounding galaxies, producing detectable signatures in velocity fields. In this way, researchers effectively use gravity itself as a surveying instrument. The universe becomes not merely something observed, but something whose invisible architecture reveals itself through motion. The investigation grows even more intricate when supernovae enter the picture. Certain types of exploding stars, particularly Type 1a supernovae, serve as standardizable candles because their intrinsic brightness can be estimated with remarkable precision. Comparing intrinsic brightness to observed brightness allows astronomers to determine distances independently of redshift. These measurements create another route toward understanding cosmic structure. If local density variations affect expansion rates, traces of those effects may appear in supernova observations. Consequently, supernova surveys have become central to debates surrounding local underdensities and the broader question of whether our cosmic neighborhood differs significantly from average conditions. What emerges from all these techniques is not a single measurement, but a convergence of independent lines of inquiry. Galaxy counts, luminosity densities, weak lensing, peculiar velocities, redshift surveys, supernova distances, and numerical simulations all contribute pieces of the puzzle. The scientific process resembles assembling a map from overlapping fragments, each fragment imperfect but collectively capable of revealing patterns that no individual method could establish alone. This redundancy is essential because cosmology operates under unique constraints. Controlled experiments on the universe are impossible. Researchers cannot create alternate universes for comparison. They cannot relocate Earth to a different region of space and repeat observations. Instead, confidence arises when multiple observational approaches point toward compatible conclusions. Yet despite these impressive methods, uncertainty remains a central feature rather than a flaw. One reason is cosmic variance, a concept reflecting the fact that observers have access to only one realization of the universe. Even if cosmological models are correct, statistical fluctuations can produce regions that appear unusually dense or unusually sparse simply by chance. Distinguishing a meaningful structural feature from a statistical fluctuation requires enormous datasets and careful analysis. This is particularly relevant when discussing structures as large as the proposed local whole. The larger the scale, the fewer independent regions exist for comparison. Consequently, uncertainties become harder to reduce. Another complication arises from survey geometry. Astronomers cannot observe every direction equally well. Dust within the Milky Way obscures portions of the sky. Instrumental limitations affect sensitivity. Selection criteria influence which objects enter catalogs. Every survey possesses boundaries and biases that must be modeled carefully. Much of modern cosmology, therefore, involves understanding not only the universe itself, but also the limitations of the tools used to study it. In a sense, astronomers spend as much effort mapping uncertainty as mapping galaxies. This process may sound painstaking, even exhausting, yet there is something quietly beautiful about it. The search for a cosmic void is not a hunt for a dramatic object waiting to be discovered behind a curtain. It is a patient reconstruction of reality from whispers of light. Every photon contributes a clue. Every redshift measurement adds a coordinate. Every distorted galaxy image reveals a trace of invisible mass. Gradually, over years and decades, a portrait emerges. It may suggest that our region of the universe contains fewer galaxies than average. It may suggest the opposite. The evidence continues evolving as observations improve, but the remarkable fact remains that human beings, confined to a single world orbiting a single star, have learned to ask whether hundreds of millions of light-years of surrounding space contain enough galaxies, and have developed the mathematical and observational machinery necessary to pursue an answer. Long before we know with certainty whether the local whole is real, that achievement itself stands as one of the most extraordinary chapters in the history of scientific thought, because it transforms darkness into geometry, distance into structure, and scattered points of ancient light into a map of the invisible landscape surrounding our place in the universe. There is a particular kind of mystery that emerges not when scientists fail to find an answer, but when they discover two answers that both appear correct and yet refuse to agree with one another. Those are often the most unsettling mysteries in science, because they do not announce themselves with dramatic anomalies or impossible observations. Instead, they appear quietly, hidden inside equations that work, measurements that have been checked repeatedly, and data sets collected by some of the most sophisticated instruments humanity has ever built. The Hubble tension belongs to this rare category. It is not a crack in a telescope mirror, nor an isolated discrepancy buried in obscure data. It is a disagreement about one of the most fundamental quantities in all of cosmology, the rate at which the universe is expanding. And what makes it especially fascinating in the context of our journey through cosmic voids is that this disagreement may be whispering something important about the region of space we happen to inhabit. To appreciate why this tension has become such a central topic in modern astrophysics, we must first travel back to the early 20th century, when astronomers were still debating whether the universe itself extended beyond the Milky Way. The idea that space might be expanding would have seemed extraordinary. Yet observations by Edwin Hubble and others gradually revealed a remarkable pattern. Distant galaxies appeared to be moving away from us, and the farther away they were, the faster they seemed to recede. This relationship eventually became known as Hubble's law. Its significance extended far beyond the motion of galaxies. It implied that space itself was stretching. The universe was not static, it was evolving. The proportionality constant describing this expansion became known as the Hubble constant, usually denoted h0. Conceptually, h0 tells us how rapidly the fabric of space expands at the present cosmic epoch. Measuring it accurately became one of the central goals of observational cosmology because its value influences estimates of the universe's age, size, density, and future evolution. For many decades, uncertainty in h0 was dominated by limitations in technology. Different measurements produced different values because instruments lacked precision, and distance estimation remained notoriously difficult. As observational astronomy improved, researchers expected these discrepancies to shrink. In many ways, they did. Yet something unexpected happened. Instead of converging toward a single value, the most precise modern measurements began separating into two distinct camps. The disagreement was not enormous, but it persisted stubbornly, despite years of scrutiny. One method suggested the universe expands at a rate around the upper 60s in kilometers per second per megaparsec. Another consistently produced values in the low to mid-70s. At first glance, the difference seems small. Yet in cosmology, where precision measurements often reach fractions of a percent, such a discrepancy becomes deeply significant. To understand why these methods differ, it helps to recognize that they are not measuring the same thing in the same way. One approach examines the nearby universe. Astronomers construct what is often called the cosmic distance ladder, a sequence of overlapping techniques that extend distance measurements progressively farther into space. Nearby stars with known parallaxes calibrate Cepheid variable stars. Cepheids calibrate Type 1a supernovae. Supernovae calibrate distances to remote galaxies. By combining these measurements with redshift observations, researchers estimate the current expansion rate. This approach effectively measures the universe directly in its relatively recent state. The second approach operates very differently. Instead of examining nearby galaxies, it studies the oldest light in existence, the cosmic microwave background. This faint radiation originated approximately 380,000 years after the Big Bang, when the universe cooled enough for photons to travel freely through space. Spacecraft such as WMAP and later the Planck mission mapped this ancient radiation with extraordinary precision. The microwave background contains subtle temperature fluctuations, reflecting density variations in the early universe. By analyzing these fluctuations within the framework of the standard cosmological model, known as lambda CDM, researchers can infer the universe's properties, including what the Hubble constant should be today. This is not a direct measurement of current expansion. It is a prediction derived from early universe conditions, evolved forward through cosmological theory. Remarkably, both methods appear internally consistent. The distance ladder measurements produce one answer. The early universe inference produces another. Neither result seems obviously flawed. Both rely on extensive cross-checking, independent teams, and increasingly precise instrumentation. It is this coexistence of apparently reliable but conflicting answers that transformed a technical discrepancy into one of the most discussed questions in contemporary cosmology. The tension became more intriguing as statistical uncertainties shrank. In science, disagreements often disappear when data improve. Here, improved precision initially seemed to sharpen the discrepancy rather than erase it. This led researchers to consider a range of possibilities. Perhaps hidden systematic errors remain embedded within one or both measurement techniques. Perhaps Cepheid calibrations contain subtle biases. Perhaps supernova environments influence luminosity estimates. Perhaps assumptions within the lambda CDM model require modification. Perhaps an unknown physical process operated in the early universe. Or perhaps, returning to the theme of our exploration, perhaps local cosmic structure is influencing observations in ways not fully accounted for. This is where the discussion intersects with the local hole and KBC void. If our region of space contains less matter than average, local expansion dynamics could differ slightly from the broader cosmic average. Gravity normally acts to slow expansion. In an underdense region, there is less matter available to produce gravitational deceleration. Consequently, galaxies within or near such a region may exhibit expansion behavior that differs subtly from expectations based on a perfectly homogeneous universe. Imagine floating within a shallow valley while attempting to infer the shape of an entire landscape. Measurements made locally may be influenced by terrain features that are invisible at larger scales. The analogy is imperfect, yet it captures the essence of the problem. If observers happen to reside inside an underdense environment, the measured Hubble rate could appear somewhat elevated relative to values inferred from the universe as a whole. The mathematics underlying this possibility emerges from relativistic cosmology and inhomogeneous solutions to Einstein's equations. Local density variations alter space-time dynamics. Expansion is not merely a global phenomenon, it possesses local structure as well. Yet the situation remains delicate. Most studies suggest that plausible local underdensities may account for only part of the observed tension, rather than all of it. Some analyses find modest effects. Others find larger contributions, depending on assumptions regarding the size and depth of the underdense region. The scientific literature, therefore, reflects an evolving conversation rather than a settled verdict. This uncertainty has inspired researchers to explore increasingly sophisticated possibilities. Some propose forms of early dark energy that briefly influence the universe before disappearing. Others investigate interactions between dark matter and radiation. Still others examine modifications to neutrino physics, variations in gravitational theory, or subtle departures from standard assumptions about cosmic homogeneity. Each proposal attempts to preserve the remarkable successes of modern cosmology while addressing the discrepancy. What makes the Hubble tension particularly captivating is that it occupies a narrow space between crisis and opportunity. The standard cosmological model remains extraordinarily successful. It explains the cosmic microwave background, large-scale structure formation, nucleosynthesis, galaxy clustering, and numerous other observations with impressive accuracy. Yet, if the tension ultimately survives, every attempt at explanation through measurement error and local environmental effects, it could indicate that some ingredient of the current model remains incomplete. Not necessarily wrong, but incomplete. Throughout the history of physics, such situations have often preceded major advances. The orbit of Mercury hinted at general relativity. Blackbody radiation hinted at quantum mechanics. Tiny anomalies sometimes illuminate profound truths. Yet caution remains essential, because science is filled with apparent anomalies that eventually dissolve under closer examination. The challenge lies in distinguishing revolutionary discoveries from subtle misunderstandings. This is why the Hubble tension generates both excitement and restraint among cosmologists. The evidence is intriguing enough to demand attention, yet complex enough to resist premature conclusions. As observations continue improving through projects such as the James Webb Space Telescope, advanced supernova surveys, baryon acoustic oscillation measurements, gravitational lensing programs, and future cosmological observatories, the picture may gradually sharpen. Some possibilities will likely be eliminated, others may gain support. For now, the tension remains unresolved. There is something almost poetic about this situation. Humanity has learned to measure distances across billions of light years, reconstruct conditions from the infancy of the universe, and map structures larger than entire superclusters. Yet, when we ask a seemingly straightforward question, how fast is the universe expanding right now? The cosmos responds with two answers. Somewhere within that discrepancy may lie a hidden systematic error. Somewhere within it may lie the influence of our local environment. Or somewhere within it may lie new physics waiting quietly beneath the surface of accepted theory. As we drift through the darkness between galaxies and contemplate the possibility that our own cosmic neighborhood may be less typical than once believed, the Hubble tension becomes more than a numerical disagreement. It becomes a reminder that understanding the universe depends not only on looking farther away, but also on understanding where we stand while doing the looking. And if the local whole truly contributes even partially to this puzzle, then the vast underdense regions surrounding us may not simply be a feature of cosmic geography. It may be one of the reasons the universe appears to speak in two voices when we ask how rapidly it is growing. If there is one idea that quietly governs nearly everything we think we know about the universe, it is the assumption that light tells the truth. Not because light possesses intention, of course, but because almost every measurement in astronomy is ultimately a measurement of light. We cannot travel to distant galaxies. We cannot touch a supercluster. We cannot place rulers across billions of light years. Instead, we sit on a small world orbiting an ordinary star and wait for ancient photons to arrive. Those photons become our evidence, our messengers, our witnesses. Yet there is a subtle distinction between a witness and reality itself. A witness reports what was seen from a particular perspective, through a particular journey, shaped by particular circumstances. And if we truly occupy a large, underdense region of the universe, then one of the most fascinating possibilities in modern cosmology emerges not from the idea that light is lying to us, but from the idea that light may be telling the truth about a local environment that is not fully representative of the larger cosmos. In other words, the deception may not come from the photons, it may come from the assumptions we attach to them. To understand this possibility, we must begin with a fact so fundamental that it often disappears into the background of astronomical thinking. Light does not travel through a static stage. It travels through an evolving space-time geometry. Every photon arriving at a telescope tonight has crossed a universe that was different when the journey began. A photon emitted from a galaxy 1 billion light-years away entered a cosmos younger than the one we inhabit now. A photon arriving from 10 billion light-years away departed when the Milky Way itself was still assembling. Consequently, every observation contains a hidden temporal dimension. Looking outward is also looking backward. This means that every cosmic map is simultaneously a map of space and a map of history. The farther light travels, the more history becomes entangled with geometry. Under ordinary circumstances, cosmologists account for this relationship through the framework of general relativity. Einstein's equations describe how matter and energy shape spacetime, and how spacetime guides the motion of matter and light. Within the standard cosmological model, the large-scale universe is treated as statistically homogeneous, allowing researchers to derive elegant relationships between distance, redshift, luminosity, and expansion. These relationships have proven extraordinarily successful. Yet they depend on assumptions regarding the average properties of the regions through which light travels. If our local environment differs significantly from those averages, then the interpretation of observations becomes more subtle. Imagine a traveler navigating a vast landscape using only echoes. The echoes themselves are real. The sounds genuinely return from distant hills and valleys. Yet if the traveler assumes the terrain is flat, when it actually contains large depressions and ridges, the resulting map may be distorted, even though every individual measurement remains accurate. Something similar can occur in cosmology. The photons may faithfully record their journey, while our interpretation of that journey depends upon assumptions regarding the geometry they crossed. One of the most important observational quantities in astronomy is redshift. As space expands, the wavelength of light stretches. The greater the expansion during a photon's journey, the larger the observed redshift. This relationship allows astronomers to infer distance and expansion history. However, expansion is not merely a global process. Local density influences local dynamics. Regions containing less matter experience weaker gravitational deceleration. Consequently, an underdense region can expand somewhat differently from a denser environment. If observers reside within such a region, galaxies may appear to recede faster than expected relative to the cosmic average. Importantly, this does not require any violation of known physics. It emerges naturally from general relativity. The universe need not be perfectly uniform for local expansion rates to differ from global averages. The effect can be understood intuitively through gravitational potential. Matter creates gravitational wells. Dense regions correspond to deeper wells. Underdense regions correspond to shallower gravitational environments. Light traveling through these structures experiences subtle changes due to evolving spacetime curvature. One manifestation of this process appears in phenomena such as the integrated Sachs-Wolf effect, where photons gain or lose energy while traversing evolving gravitational potentials. Although the effect associated with local voids is generally small, it illustrates an important principle. Light does not merely carry information about distant objects. It also carries information about the space-time landscape encountered along the way. In this sense, every photon arrives bearing traces of both source and journey. The distinction becomes increasingly important when discussing distance measurements. Consider a Type 1a supernova, one of the most valuable tools in cosmology. Because these stellar explosions exhibit relatively predictable luminosities, they function as standardizable candles. Astronomers compare intrinsic brightness to observed brightness and infer distance. Combined with redshift measurements, these distances help determine the expansion rate of the universe. Yet, if local space-time geometry differs from the assumptions built into cosmological models, the inferred relationship between distance and redshift may shift slightly. A galaxy observed through the lens of an underdense environment could appear to participate in a faster local expansion than would be inferred from observations averaged across larger cosmic volumes. The photons themselves remain honest. The challenge lies in interpreting what honesty means when viewed from inside a cosmic depression. Another subtle effect emerges through peculiar velocities. In an idealized, homogeneous universe, galaxies recede smoothly according to the Hubble flow. Reality is more complicated. Galaxies possess additional motions generated by gravitational interactions with surrounding matter distributions. These peculiar velocities create deviations from pure expansion. Large, underdense regions tend to push matter outward relative to their centers because surrounding denser regions exert stronger gravitational attraction. As a result, galaxies near the boundaries of a void may exhibit coherent motions away from the underdense interior. Observers embedded within such a structure might therefore measure recession patterns influenced by local environmental dynamics. Again, no deception occurs at the level of observation. The complexity arises when separating local gravitational effects from global cosmological behavior. The challenge becomes even more profound when considering the philosophical structure of cosmological inference. Astronomers do not measure the expansion history of the universe directly. They infer it from observations interpreted through theoretical frameworks. Every measured quantity passes through layers of modeling. Distances depend on calibration methods. Expansion rates depend on distance estimates. Cosmological parameters depend on expansion rates. Models connect all these elements into a coherent picture. This process is extraordinarily powerful, but it also means that small environmental effects can propagate through multiple layers of interpretation. A local underdensity affecting observed distances by a few percent may ultimately influence estimates of larger cosmological quantities. This possibility explains why the local hole hypothesis attracted attention within discussions of the Hubble tension. Researchers began asking whether local structure could bias measurements derived from nearby galaxies and supernovae. If so, some portion of the discrepancy between local and early universe expansion estimates might reflect our position within the cosmic web, rather than entirely new physics. Current evidence suggests that local underdensities alone may not fully explain the tension, but the investigation revealed something intellectually profound. It demonstrated that understanding the universe requires understanding where we are inside it. The observer cannot always be separated completely from the observation. In some cases, the geometry surrounding the observer becomes part of the measurement itself. There is also a deeper layer to this story, one that touches the nature of cosmic horizons and observational limits. Because light travels at a finite speed, every observer occupies the center of a personal, observable universe. No observer can access information beyond the distance light has traveled since the beginning of cosmic expansion. Consequently, all cosmological conclusions arise from a finite sample of reality. This limitation introduces what cosmologists call cosmic variance, the unavoidable uncertainty associated with observing only one realization of the universe. If our observable region contains unusual, large-scale structures, those structures become part of the observational record from which theories are constructed. We cannot step outside the observable universe to compare perspectives. We possess only the view available from here. In that sense, every cosmological measurement carries an unavoidable element of locality. As the night deepens and the mind drifts farther into the darkness between galaxies, the question changes subtly. We begin by asking whether light has deceived us. Yet the more careful answer may be that light reveals exactly what exists along its path. The real challenge lies in distinguishing local truths from universal truths. A photon arriving from a distant galaxy tells us about the galaxy, the intervening spacetime, the distribution of matter encountered during the journey, and the location from which the observation is made. All those factors become woven together into a single signal. Untangling them requires mathematics, observation, patience, and humility. If we do inhabit a vast cosmic void, then the lesson may not be that astronomy has been fooled. The lesson may be that reality is more context-dependent than simple diagrams suggest. Light has always been faithful. It has carried ancient messages across billions of years without alteration of intent. Yet those messages arrive through a universe whose geometry is alive, structured, evolving, and uneven. Understanding them requires more than reading the photons. It requires understanding the cosmic landscape through which they traveled. And somewhere within that landscape, perhaps surrounding us at this very moment, may lie a quiet, underdense region whose influence is subtle enough to escape casual notice, yet significant enough to shape humanity's measurement of the expanding universe itself. If the possibility of a vast cosmic void surrounding our region of the universe is real, then an even deeper question emerges from the darkness behind it. What could possibly create something so enormous? What mechanism could sculpt a region hundreds of millions, perhaps even billions of light-years across, and leave it with significantly less matter than the cosmic average? At first glance, the existence of such a structure feels almost impossible. Human intuition struggles with scales this large, because nearly every process familiar to daily experience operates locally. Mountains form through tectonic forces. Storms emerge from atmospheric dynamics. Rivers carve valleys over geological time. Yet cosmic voids exist on scales so immense that even entire superclusters appear as minor features within their boundaries. To understand how such structures might arise, we must travel backward through cosmic history, not merely to the birth of galaxies or stars, but to a time when neither existed, when the universe itself was young enough that the distinction between emptiness and structure had not yet emerged. The remarkable answer suggested by modern cosmology is that the largest voids in existence may ultimately trace their origins to fluctuations so small that they began as microscopic differences in density during the earliest moments of cosmic history. This idea is one of the most extraordinary consequences of contemporary physics, because it implies that some of the largest structures ever observed may owe their existence to processes operating on scales smaller than atoms. To see how this can be possible, we begin with the inflationary paradigm, a framework developed to explain several puzzling features of the observable universe. According to inflationary models, a tiny fraction of a second after the beginning of cosmic expansion, the universe may have undergone a period of extraordinarily rapid exponential growth. During this interval, space-time itself expanded at a rate vastly exceeding the speed at which light could traverse the growing distances, not violating relativity, because it was space expanding rather than objects moving through space. This inflationary phase had profound consequences. Quantum fluctuations, normally confined to microscopic scales, were stretched across cosmic distances. Tiny variations in energy density became embedded into the fabric of the young universe. When inflation ended, those variations remained as faint imprints scattered throughout space. At the time, the differences were astonishingly small. Measurements of the cosmic microwave background suggest density variations of roughly 1 part in 100,000. Yet gravity possesses a unique characteristic. It never stops working. Even the slightest excess of matter exerts a stronger gravitational pull than its surroundings. Over billions of years, these tiny differences become amplified. Regions that began slightly denser attract more matter, growing increasingly dense. Regions that began slightly less dense lose matter to neighboring regions and become increasingly empty. In this sense, the formation of a cosmic void is not a separate process from the formation of galaxies. Both emerge from the same initial conditions. They are opposite expressions of the same gravitational evolution. One region gains matter, another loses it. One becomes a filament or cluster, the other becomes a void. What makes this process especially elegant is that gravity generates structure through asymmetry rather than symmetry. If matter were distributed perfectly uniformly, gravity would have nothing to amplify. No galaxies would form, no clusters would emerge. The universe would remain smooth and featureless. Structure exists precisely because the early universe was not perfectly uniform. In mathematical terms, cosmologists often describe these initial variations using a density contrast parameter, commonly represented by delta, which compares local density to the average cosmic density. Positive values correspond to overdense regions. Negative values correspond to underdense regions. The subsequent evolution of these fluctuations can be modeled through perturbation theory during early stages and numerical simulations once nonlinear gravitational effects become important. As time progresses, the asymmetry intensifies. Dense regions collapse and concentrate matter. Underdense regions evacuate themselves. The contrast grows. Yet gravity alone does not tell the entire story. Dark matter plays a central role. Although invisible, dark matter dominates the matter budget of the universe and appears to provide the gravitational scaffolding upon which visible structures form. In simulations containing only ordinary matter, the observed cosmic web is difficult to reproduce accurately. When dark matter is included, filamentary structures, clusters, and voids emerge with remarkable similarity to real observations. This occurs because dark matter begins clumping earlier than ordinary matter. Prior to recombination, ordinary matter remained strongly coupled to radiation. Dark matter did not. As a result, dark matter structures began developing before atoms could form stable neutral configurations. These early dark matter concentrations later guided the accumulation of ordinary matter, influencing where galaxies would eventually appear. Consequently, when discussing the origins of giant voids, we are simultaneously discussing the behavior of a substance that has never been directly observed in laboratory conditions. The largest empty regions in the universe may owe much of their existence to the dynamics of matter we cannot see. As cosmic evolution continues, voids experience a fascinating form of growth distinct from the collapse of clusters. A galaxy cluster becomes denser through accretion. A void becomes emptier through evacuation. Matter gradually migrates towards surrounding filaments and walls. The interior density decreases relative to the average. Because gravitational deceleration is weaker inside underdense regions, those regions tend to expand faster than their surroundings. This differential expansion causes voids to grow. In many simulations, neighboring smaller voids merge together over time, producing larger and larger underdense regions. This process, sometimes described as void hierarchy evolution, resembles the merging of soap bubbles. Small voids coalesce into larger cavities. The resulting structures can reach extraordinary dimensions. In this framework, a giant void does not necessarily require a unique cause. It may emerge naturally from the cumulative evolution of many smaller underdensities over billions of years. Yet the possibility of a local hole, or KBC void, introduces a subtle complication. The question is no longer whether voids can form. Standard cosmology clearly predicts that they can. The question becomes whether a void of the proposed size and characteristics is statistically expected within the lambda CDM framework. Here, the scientific conversation becomes more nuanced. Some researchers argue that large underdense regions fall comfortably within the range of structures expected from cosmic variance. Others suggest that certain reported void sizes appear less common within standard simulations, potentially motivating closer investigation. The debate does not center on whether voids exist, but on how unusual a particular void might be. This distinction is crucial because cosmology is fundamentally statistical. Rare events occur even in perfectly valid models. Determining whether a structure is improbable enough to challenge existing theory requires careful comparison between observation and simulation. Another layer of complexity emerges when considering baryon acoustic oscillations, faint imprints left behind by pressure waves propagating through the hot plasma of the early universe. These oscillations established a characteristic scale that remains visible in the large-scale distribution of galaxies today. By measuring this scale, astronomers gain a powerful tool for testing cosmological models. The distribution and evolution of voids interact with these acoustic signatures in subtle ways, providing additional constraints on theories of structure formation. In effect, the universe retains a memory of its earliest conditions, and voids become one of the places where that memory can still be read. Some of the most intriguing possibilities extend beyond conventional gravitational evolution. Certain speculative inflationary models allow enhanced fluctuations at specific scales. Alternative dark matter scenarios could influence how structures grow. Modified gravity theories may alter void dynamics. There have even been discussions of whether primordial features generated during inflation could leave detectable imprints on the distribution of large-scale voids. None of these ideas currently commands broad consensus, yet they illustrate how giant, underdense regions serve as laboratories for testing the foundations of cosmology. A void is not merely an absence of galaxies. It is a probe of the earliest moments of cosmic history. What makes this realization so profound is that the emptiest places in the universe may preserve information about its most energetic epoch. The path connecting inflationary quantum fluctuations to present-day voids spans nearly 14 billion years. It crosses epochs of radiation domination, matter domination, galaxy formation, dark matter clustering, and accelerated expansion driven by dark energy. Every stage contributes to the final architecture. The giant cavities visible today are therefore not accidents appearing suddenly in an otherwise orderly universe. They are the cumulative outcome of an unbroken chain of physical processes extending from the earliest measurable moments of cosmic time to the present day. If we truly inhabit a large, underdense region, then the emptiness surrounding us would not represent a failure of structure formation. It would represent structure formation operating exactly as nature allows, amplified across scales so vast that human intuition struggles to comprehend them. And perhaps that is the most beautiful aspect of the story. The giant void, which at first appears as a missing feature, ultimately reveals itself as a product of abundance rather than absence. It is the consequence of gravity patiently sorting matter across billions of years, of dark matter guiding invisible currents through space-time, of inflation stretching microscopic fluctuations into cosmic blueprints, and of the universe continuously transforming tiny asymmetries into monumental architecture. In that sense, the largest empty spaces in existence are not empty stories at all. They are the visible shadows cast by the deepest processes that shaped the cosmos from the very beginning. By the time we arrive at this question, something subtle has already happened. The cosmic void is no longer merely an empty region on a map of galaxies. It is gradually transformed into a test of our deepest assumptions about reality. In the beginning, the possibility seemed straightforward. Perhaps our local neighborhood contains fewer galaxies than average. Perhaps we happen to live inside a large, underdense region. Yet as we followed that possibility through observations, gravitational dynamics, redshift measurements, distance ladders, and the Hubble tension, the discussion expanded into something much larger. We began asking whether the existence of such a void might challenge the standard model of cosmology itself. And whenever science reaches a moment like this, caution becomes as important as curiosity, because history contains many examples of apparent contradictions that ultimately strengthened existing theories, just as it contains a few rare examples that forced those theories to evolve. To understand where cosmic voids fit into this landscape, we must first understand what exactly is meant by the standard model of cosmology. Known as lambda CDM, the model combines several key ingredients into a single mathematical framework. The symbol lambda represents dark energy, the mysterious component associated with the accelerated expansion of the universe. CDM stands for cold, dark matter, the invisible matter that appears to dominate gravitational structure formation. Together with ordinary matter, radiation, and the equations of general relativity, these components create a model capable of explaining an extraordinary range of observations. The cosmic microwave background, the large-scale distribution of galaxies, the abundance of light elements, gravitational lensing, galaxy clustering, baryon acoustic oscillations, and the overall expansion history of the cosmos all emerge from this framework with remarkable consistency. It is difficult to overstate the success of lambda CDM. In terms of predictive power, it stands among the most successful scientific models ever developed. Yet success does not imply completeness. Every model operates within assumptions. Some assumptions are explicit. Others remain so familiar that they become nearly invisible. One of the most important is the cosmological principle, the idea that when averaged over sufficiently large scales, the universe is statistically homogeneous and isotropic. In simpler terms, the universe should not possess a preferred location or preferred direction. Local irregularities certainly exist. Galaxies, clusters, filaments, and voids are obvious examples. However, on scales large enough, these irregularities are expected to average out. This assumption allows cosmologists to describe the universe using elegant mathematical solutions derived from Einstein's equations. Without it, the equations become vastly more complicated. The possibility of an enormous local void enters the conversation because it touches directly on the scale at which homogeneity emerges. If the local hole, or KBC void, were sufficiently large and sufficiently deep, some researchers have wondered whether our observational perspective might be more unusual than standard assumptions typically allow. This does not automatically invalidate lambda CDM. Rather, it raises questions about whether local observations can be interpreted as straightforward representatives of the universe as a whole. The distinction is subtle, but crucial. A theory can remain fundamentally correct, while specific observations become biased by local environmental effects. In fact, this possibility is one reason void studies have attracted sustained attention. They offer a way to test whether apparent anomalies arise from new physics or from cosmic geography. Yet, the conversation becomes more interesting when we ask a different question. Suppose the void is real. Suppose it is larger than expected. At what point would it genuinely challenge the standard cosmological model? To answer this, cosmologists turn to simulations. Modern numerical simulations evolve billions of particles, representing dark matter and ordinary matter through cosmic time. Starting from initial conditions consistent with observations of the early universe, these simulations generate structures remarkably similar to those observed today. Filaments appear, clusters emerge, voids grow. The resulting cosmic web resembles reality with surprising fidelity. Therefore, the existence of voids itself is not a problem for lambda CDM. On the contrary, voids are predicted by it. The challenge arises only if observed voids systematically exceed the size, depth, or frequency expected from simulations. In that scenario, researchers would need to determine whether the discrepancy reflects statistical chance, observational bias, incomplete modeling, or genuinely new physics. One reason this question remains unresolved is that giant structures occupy an awkward statistical regime. Small structures are abundant. Large structures are rare. Extremely large structures are exceptionally rare. The larger the object under investigation, the fewer examples exist for comparison. This makes probability estimates difficult. Cosmologists must determine whether a particular structure lies comfortably within the tail of a known distribution or whether it occupies territory requiring theoretical revision. The distinction often depends on assumptions regarding survey completeness, matter density measurements, and statistical methodology. Consequently, discussions surrounding large voids frequently involve probability distributions rather than definitive yes or no conclusions. Another layer of complexity emerges from the role of dark energy. Lambda CDM attributes accelerated cosmic expansion to dark energy, represented mathematically by the cosmological constant. This component influences how structures evolve over billions of years. As dark energy becomes increasingly dominant, the growth of large-scale structure slows. Voids continue expanding, but their evolution changes. Because void behavior depends on both gravity and cosmic expansion, underdense regions provide a valuable testing ground for dark energy models. Some alternative cosmologies predict different void properties than lambda CDM. For example, certain modified gravity theories alter how gravitational forces behave in low-density environments. Since voids contain less matter and weaker gravitational screening effects, deviations from standard gravity could become more visible there than inside dense galaxy clusters. In this sense, voids act as natural laboratories. Their emptiness simplifies the environment, making subtle physical effects easier to detect. Researchers have therefore examined whether observed void properties align with predictions from general relativity and lambda CDM, or whether they hint at alternative explanations. So far, the evidence remains broadly compatible with the standard framework, though investigations continue. The Hubble tension introduces another pathway through which voids might interact with cosmological theory. If local underdensities influence expansion measurements, then some portion of the tension could potentially arise without requiring new fundamental physics. This possibility is appealing because it preserves the standard cosmological model while explaining observational discrepancies through environmental effects. Yet most current analyses suggest that plausible local voids may not fully resolve the tension. The effect often appears too small to account for the entire difference between local and early universe measurements. This does not eliminate the importance of voids. Rather, it shifts their role from complete explanation to partial contributor. The distinction matters because scientific debates are rarely settled by a single factor. Multiple influences may operate simultaneously. Small local effects, subtle systematic uncertainties, and new physics could all contribute in varying degrees. Some of the most intriguing challenges to lambda CDM arise not from individual observations, but from combinations of anomalies. Researchers sometimes discuss tensions involving structure growth rates, clustering amplitudes, and expansion measurements. Each discrepancy alone may appear manageable. Together, They motivate closer scrutiny of the model's assumptions. Yet, it is important to recognize that lambda CDM has survived many such examinations. The model possesses extraordinary explanatory power. Any proposed replacement must not only explain one anomaly, but also preserve the vast range of successful predictions already achieved. This requirement creates a high evidentiary threshold. Revolutionary alternatives are possible, but they must outperform a framework that has accumulated decades of observational support. There is a deeper philosophical lesson hidden within this discussion. Scientific models are not judged solely by whether every observation aligns perfectly. They are judged by their ability to organize evidence, generate successful predictions, and remain adaptable when confronted with new data. The existence of tension does not imply failure. In many cases, tension is precisely what drives progress. Cosmology advances because observations continue probing regimes where theoretical assumptions can be tested. Voids occupy one of those regimes. They challenge researchers to examine whether concepts such as homogeneity, dark energy, gravity, and structure formation remain robust under increasingly precise scrutiny. In that sense, a giant void functions less like an enemy of the standard model and more like an examiner presenting difficult questions. Sometimes the model answers successfully. Sometimes the answers reveal uncertainties, requiring further investigation. Either outcome expands knowledge. As we drift farther into the silence of the cosmic web, the image becomes strangely beautiful. The emptiest regions of the universe, places containing fewer galaxies than average, become arenas where some of the most profound ideas in physics are tested. Their darkness is not a lack of information, but a source of it. The question is no longer whether voids exist. We know they do. The question is whether the largest and most influential among them fit comfortably within the expectations of lambda CDM, or whether they hint at deeper layers of cosmic structure still waiting to be understood. At present, the balance of evidence suggests that the standard cosmological model remains remarkably resilient. Yet resilience is not the same as finality. The universe has surprised astronomers many times before. Every generation has eventually discovered that reality contains subtleties hidden beyond its most successful theories. Whether cosmic voids will ultimately become one of those subtleties remains uncertain. For now, they occupy a fascinating middle ground, large enough to test the foundations of cosmology, mysterious enough to inspire debate, and quiet enough to remind us that sometimes the greatest questions emerge not from what fills the universe, but from what appears to be missing from it. The deeper we travel into the mystery of a possible cosmic void surrounding our region of the universe, the more we begin to notice a subtle transformation in the question itself. At first, the puzzle appeared geographical. Was there really less matter around us than expected? Then it became observational. Could a local underdensity influence how we measure cosmic expansion? Later, it became theoretical. Could such a structure challenge assumptions embedded within the standard cosmological model? But eventually, every path seems to converge toward an even more profound horizon, one that has haunted cosmology for decades. What if the void is not merely a structure within the universe, but a clue about the deeper machinery governing the universe itself? What if the apparent emptiness around us is somehow connected to dark matter, dark energy, or physical laws that remain invisible to current theories? These possibilities occupy a delicate space between established science and active research. None have achieved broad consensus. Yet they are explored seriously because they emerge naturally whenever observations begin pushing against the limits of existing models. To appreciate why, we must first acknowledge an extraordinary fact. According to the current cosmological framework, everything directly visible, every star, every planet, every nebula, every galaxy, every human being who has ever lived, accounts for only a small fraction of the total cosmic energy budget. Roughly 5% appears to consist of ordinary baryonic matter. The rest belongs to two mysterious components whose physical nature remains uncertain. Dark matter contributes roughly a quarter of the total. Dark energy appears to dominate the remainder. The standard model of cosmology successfully describes how these components influence cosmic evolution, yet describing behavior is not the same as understanding essence. In a profound sense, modern cosmology works astonishingly well, while simultaneously admitting that most of the universe consists of things not yet fully understood. This creates fertile ground for deeper possibilities whenever unexpected observations arise. Consider dark matter first. Its existence was not proposed to explain cosmic voids. Rather, it emerged from multiple independent lines of evidence. Galaxy rotation curves revealed stars moving too rapidly to be gravitationally bound by visible matter alone. Galaxy clusters displayed gravitational effects exceeding expectations based on luminous material. Gravitational lensing observations repeatedly pointed toward unseen mass. Large-scale structure simulations required an invisible component to reproduce the observed cosmic web. Together, these clues formed a compelling case for dark matter. Yet, despite decades of effort, its particle nature remains elusive. Numerous candidates have been proposed, including weakly interacting massive particles, axions, sterile neutrinos, and more exotic possibilities. Direct detection experiments continue searching, but definitive confirmation remains absent. This uncertainty leaves room for an intriguing question. If dark matter governs the growth of cosmic structure, could unusual void properties reveal something unexpected about dark matter itself? Some theoretical models suggest they might. In conventional cold dark matter scenarios, structure formation proceeds through hierarchical growth. Small structures form first and gradually merge into larger systems. Voids emerge naturally through gravitational evolution. However, alternative dark matter candidates can modify this process. Warm dark matter, for example, suppresses the formation of small-scale structures because its particles possess higher primordial velocities. Self-interacting dark matter introduces additional dynamical effects. Ultralight dark matter models produce wave-like behavior on astrophysical scales. Each scenario leaves subtle fingerprints on the distribution of matter. Voids become especially valuable in this context because they represent environments where gravitational evolution proceeds under relatively simple conditions. Dense clusters contain numerous competing influences. Voids offer cleaner laboratories. Their very emptiness allows small physical effects to stand out more clearly. Consequently, researchers increasingly study void statistics as potential probes of dark matter physics. The possibility remains speculative, yet it illustrates how an underdense region can become a window into phenomena operating far beyond direct observational reach. Dark energy introduces an even deeper layer of mystery. Unlike dark matter, which clusters gravitationally, dark energy appears remarkably smooth. Its defining feature is its influence on cosmic expansion. Observations of distant supernovae during the late 20th century revealed that the expansion of the universe is accelerating rather than slowing down. Within the lambda-CDM framework, this acceleration is attributed to the cosmological constant, represented by lambda. Mathematically, The cosmological constant behaves like a uniform energy density intrinsic to space itself. Yet this elegant solution introduces one of the greatest theoretical puzzles in modern physics. Quantum field theory predicts vacuum energy values enormously larger than the observed cosmological constant. The discrepancy is so extreme that many physicists regard it as one of the most significant unresolved problems in fundamental science. Against this backdrop, any anomaly involving cosmic expansion naturally attracts attention. If local voids influence expansion measurements, researchers must determine whether observed discrepancies reflect environmental effects, dark energy behavior, or something else entirely. Some alternative models replace the cosmological constant with dynamic fields whose properties evolve over time. Collectively known as quintessence models, these frameworks allow dark energy to vary throughout cosmic history. Other theories propose interactions between dark matter and dark energy. Still others explore modifications to gravity itself. In each case, voids become important because low-density environments may amplify differences between competing models. The accelerated growth of underdense regions can reveal subtle departures from standard predictions. Thus, a giant void may serve not merely as a structure to be explained, but as an instrument capable of testing the nature of cosmic acceleration. Yet perhaps the most intriguing possibility emerges when researchers consider that neither dark matter nor dark energy may fully resolve certain observational tensions. This leads to the territory often described, somewhat cautiously, as new physics. The phrase sounds dramatic, but within scientific practice, it usually refers to a simple idea. Existing theories may be incomplete. Historically, new physics has often emerged when persistent discrepancies resisted explanation within established frameworks. Mercury's orbital anomaly contributed to the development of general relativity. The ultraviolet catastrophe helped inspire quantum mechanics. Small cracks occasionally reveal deeper foundations. In contemporary cosmology, discussions of new physics often revolve around the early universe. One prominent example involves the concept of early dark energy. In these models, an additional energy component briefly influences cosmic evolution before fading away. Such behavior could alter conditions inferred from the cosmic microwave background and potentially reduce tensions between early universe and late universe measurements. Other proposals involve additional relativistic particles, modified neutrino properties, hidden sectors, extrascalar fields, or entirely new interactions operating during the universe's infancy. None of these possibilities currently enjoys decisive empirical support, yet they remain under active investigation because the universe continues presenting puzzles that standard assumptions do not completely eliminate. What makes this discussion especially relevant to cosmic voids is that structure formation links all these phenomena together. The distribution of matter visible today reflects the cumulative outcome of every major process operating throughout cosmic history. Inflation-shaped primordial fluctuations. Dark matter guided gravitational growth. Dark energy influenced expansion. Gravity orchestrated the evolution of structure. If any ingredient differs from current expectations, traces may appear in the architecture of the cosmic web itself. Voids, therefore, function as historical records. Their sizes, shapes, density profiles, motions, and distributions preserve information about billions of years of cosmic evolution. Reading those records correctly is difficult, but the potential reward is enormous. They may contain clues inaccessible through other observational channels. There is also a more philosophical possibility that occasionally surfaces within these discussions. The standard cosmological model assumes that the laws of physics remain constant across observable space and cosmic time. This assumption is strongly supported by evidence and remains one of the foundations of modern science. Yet researchers continue testing it because science advances through verification rather than certainty. If fundamental constants evolved slightly over cosmic history, or if gravity behaves differently on the largest scales, some signatures might emerge in large-scale structures, including voids. Such ideas remain speculative and currently lack compelling evidence, but they illustrate how deeply the investigation can reach. A void is no longer merely an empty region between galaxies. It becomes a stage upon which some of the largest questions in physics can be explored. As the night grows quieter and the cosmic web stretches outward beyond imagination, it becomes clear that the mystery of a possible local hole is not ultimately about missing galaxies. It is about whether those missing galaxies point towards something deeper. Perhaps the answer will remain entirely within the framework of standard cosmology. Perhaps improved observations will reveal that local underdensities are ordinary consequences of structure formation. Yet perhaps the investigation will illuminate new aspects of dark matter, new insights into dark energy, or entirely unexpected features of the universe's underlying laws. At present, no evidence compels such conclusions. Scientific caution demands restraint, but curiosity demands exploration. Between those two forces, cosmology continues moving forward, and somewhere within the immense silence of the largest voids, among regions where matter is scarce and galaxies grow rare, there may exist clues not merely about where matter failed to gather, but about what the universe truly is beneath the visible surface of its stars. As we arrive at the final question, it becomes clear that the answer is both simpler and more profound than it first appeared. After traveling through the architecture of the cosmic web, through the mathematics of large-scale structure formation, through galaxy surveys, gravitational lensing, peculiar velocities, dark matter, dark energy, the Hubble tension, and the possibility of new physics, we return to the original mystery with a deeper appreciation for what is actually being asked. Are we truly living inside a vast, underdense region of the universe? Are we, as the title suggested at the beginning of this journey, inside a cosmic hole? The most scientifically honest answer available today is neither a confident yes nor a definitive no. It is a carefully measured possibility. Current observations suggest that our local cosmic environment may indeed be somewhat less dense than the cosmic average across certain scales. Multiple surveys over the past several decades have reported evidence consistent with a local underdensity. Various analyses have found fewer galaxies than expected within large volumes surrounding the Milky Way. Some studies have proposed structures such as the local hole or the KBC Void to describe this apparent deficit. Yet the magnitude, extent, statistical significance, and cosmological implications of that underdensity remain subjects of ongoing investigation. No broad scientific consensus currently exists that we inhabit a giant void large enough to fundamentally overturn modern cosmology. At the same time, the possibility has not disappeared under scrutiny. It continues to occupy a fascinating space within contemporary research, a place where observation, theory, and uncertainty coexist. Yet something remarkable happens when we pause and look beyond the immediate question. The deeper lesson of this investigation may not concern the existence of a particular void at all. Instead, it concerns how humanity learns about the universe. Consider what has been required simply to ask the question. The local hole, if it exists, cannot be seen directly. No observer looking into the night sky would notice its presence. The stars appear normal. The Milky Way appears normal. Nearby galaxies continue shining across the darkness. The underdensity emerges only through statistical analysis performed across immense cosmic distances. It is detected not through direct vision, but through comparison, inference, and mathematical reconstruction. This fact alone reveals something extraordinary about modern science. We have reached a point where our questions concern not merely the existence of galaxies, but the average density of matter across hundreds of millions of light years. We are examining structures so large that individual galaxies become tiny data points within larger patterns. The scale of human inquiry has expanded almost beyond comprehension. Yet perhaps the most intriguing realization is that the original phrase, cosmic whole, subtly changes meaning as our understanding deepens. At the beginning, the phrase evokes emptiness. It suggests absence, darkness, and missing matter. By the end, the void reveals itself as something far richer. A cosmic void is not truly empty. Dark matter may still flow through it. Radiation still crosses it. Gravity still shapes it. Galaxies still inhabit it, though in smaller numbers. Space itself continues expanding within it. In many ways, a void is not a place where nothing exists. It is a place where the universe expresses a different aspect of its structure. The cosmic web requires both concentrations and evacuations, both clusters and cavities, both abundance and scarcity. Remove the voids and the web itself disappears. The emptiest regions become essential components of the largest architecture ever discovered. This realization carries an unexpected philosophical resonance. Throughout history, human beings have repeatedly mistaken absence for insignificance. Empty deserts were once viewed as wastelands before revealing complex ecosystems. Empty space was once imagined as a passive backdrop before physics revealed it to be dynamic and structured. Likewise, cosmic voids initially appeared to be regions where little happened. Yet modern cosmology increasingly treats them as powerful laboratories capable of testing gravity, dark matter, dark energy, and the geometry of the universe itself. Their apparent emptiness amplifies their scientific value. In a strange way, the less they contain, the more they reveal. There is another reason the possibility of a local void continues to fascinate cosmologists. It touches one of the oldest themes in scientific history, the relationship between observer and environment. From the time of Copernicus onward, science has gradually removed humanity from positions of cosmic privilege. Earth is not the center of the solar system. The solar system is not the center of the galaxy. The Milky Way is not the center of the universe. Yet the local whole reminds us that location still matters, not because our position is special in any metaphysical sense, but because every measurement originates somewhere. The observer always occupies a specific region of space-time. If local structure influences observation, then understanding our environment becomes part of understanding reality itself. In this respect, the investigation of a cosmic void becomes an exercise in intellectual humility. It reminds us that observations are never entirely detached from context. The universe is not viewed from nowhere. It is viewed from here. One of the most beautiful aspects of modern cosmology is that it embraces this challenge rather than avoiding it. Researchers continuously ask whether local conditions affect measurements, whether assumptions remain valid, whether hidden biases exist, whether models require refinement. This willingness to question even successful theories is not a weakness. It is one of the reasons science progresses. The local whole debate, therefore, represents something larger than a dispute over galaxy counts. It demonstrates the self-correcting nature of scientific inquiry. Every observation becomes an invitation to test assumptions. Every anomaly becomes an opportunity to learn. Even if future evidence ultimately shows that local underdensities are smaller than some current estimates suggest, the investigation will still have served an important purpose. It will have sharpened measurements, improved models, and deepened understanding of the cosmic web. Meanwhile, the broader mysteries remain. Dark matter continues exerting gravitational influence, while revealing little about its underlying nature. Dark energy continues driving accelerated expansion, while resisting complete explanation. The Hubble tension continues encouraging new observations and theoretical innovation. The largest structures in the universe continue stretching across scales so immense that human intuition struggles to visualize them. Against this backdrop, the possibility of living within a vast, underdense region becomes part of a larger story. A story not about certainty, but about exploration. The universe remains understandable enough to investigate, yet mysterious enough to surprise us. Perhaps that balance is what makes cosmology so compelling.
It offers answers while simultaneously revealing deeper questions waiting beyond them. And so, as the stars drift silently above, and the immense cosmic web extends far beyond the reach of ordinary imagination, the final answer emerges with a quiet elegance. We may indeed inhabit a region of the universe that contains less matter than average. Current evidence leaves that possibility open. Some observations support it, others continue refining its scope. The question remains active rather than settled. Yet, whether the local whole ultimately proves large, small, significant, or largely statistical, the deeper truth remains unchanged. We live inside a universe whose structure is far more intricate than early generations of astronomers ever imagined. A universe where emptiness evolves, where gravity sculpts darkness into geometry, where invisible matter guides visible galaxies, where ancient photons carry information across billions of years, and where even the largest voids may preserve clues about the earliest moments of existence. In that sense, the most important discovery is not that we might be living inside a cosmic hole. It is that the universe has become strange enough, beautiful enough, and understandable enough that humanity can seriously ask such a question at all. And somewhere beyond the nearest galaxies, beyond the local clusters, beyond the faint walls of the cosmic web, the answer continues unfolding in silence as the universe expands into the future, carrying its mysteries with it. And so, whether we truly live inside a cosmic void or not, the universe remains far stranger and more beautiful than we once imagined. Thank you for spending this journey with Sleepy Space. If you enjoyed tonight's exploration, please subscribe, and I'll see you beneath the stars in the next